The first law of thermodynamics is going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now in this lesson, we're going to talk about the first law of thermodynamics, which is going to provide for us a mathematical relationship between the change in internal energy, heat, and work. We'll talk about how to calculate heat and work, and also how to calculate heat, work, and the change in internal energy for 4 different types of processes: isobaric, isochoric, adiabatic, and isothermal. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So conceptually, we often explain the first law of thermodynamics and say that energy cannot be created or destroyed, or we simply call it the conservation of energy. But it turns out it has a little more mathematical definition to that, and it's summed up by this equation right here: delta U equals Q plus W, where delta U is the change in internal energy, Q is heat, and W is work. And in this case, we gotta remember what internal energy is, or kind of come up with a better working definition. We saw it just a little bit in the last chapter when we talked about ideal gases. And for a ideal monatomic gas, we found out that the translational kinetic energy was equal to 3/2 RT. Well, it turns out internal energy is the sum total of all the kinetic and potential energies of a system. Well, for a monatomic ideal gas, all it has is translational kinetic energy. There's no potential energy, there's no other type of kinetic energy like rotational or anything like that. And so as a result, this is also equal to the internal energy for 1 mole of a monatomic ideal gas. Now, if again you get a diatomic, or if it's not behaving ideally or something like this, then this is not going to be satisfactory, but nice convenient reference point. Now, most of the time we're going to have difficulty actually calculating an actual absolute value for internal energy. But what we can do most of the time is calculate a change in internal energy with this lovely equation. If we kind of take a look at what this equation means, so we're going to define something we're investigating, and we're going to refer to the thing that we're investigating as the system. And then everything else in the universe outside of what we've defined as the thing we're investigating, we're going to refer to as either the surroundings or the environment or something like that, most commonly probably called the surroundings. So we're going to see this exchange of energy between the system and the surroundings. And that's going to happen in one of 2 ways. And so the first way is heat, and this is the one that's going to make a little more intuitive sense. And you can either have heat entering the system from the surroundings, in which case Q would be greater than 0 or positive, or you can have heat leaving the system into the surroundings, in which case Q would be negative. And so everything here is defined mathematically in terms of the system. If the system gains energy, that's when Q is positive. If the system loses energy, that's when Q is negative. So everything's defined relative to the system. Now on the other side, we can talk about work. And in this case, things are going to be a little less clear, but if energy is entering the system again in one way, shape, or form, then we're going to define work as positive, and if energy is leaving the system, we'll define work as negative. And I say energy, it's really not easy to say that energy is entering or leaving the system. It's really work is either being done on the system, and if work's being done on the system, who's doing the work? Well, this something in the surroundings is. And so we can say that work is being done by the surroundings on the system, and when that happens, when work is done on the system ultimately gains internal energy. That's when W is positive. But you can also have it the other way around. It could be the system doing work on the surroundings. So just like when you do work and you lose energy, when the system does work, it loses internal energy as well. So in freeing up some energy to do that work, it had to use up some of its sum total of kinetic and potential energy along the way. Cool, so that you gotta kind of know the words there. So if the system does work on the surroundings, W is negative. If the surroundings do work on the system, then W is going to be positive. It's all defined, again, relative to the system gaining or losing internal energy. Now, one thing to note, sometimes you'll see this equation written a little bit different. So oftentimes from the perspective of an engineer, and you might see it delta U equals Q minus W. And in that case, they're actually defining W not as the W of the system, but the W of the environment, the W of the surroundings. And the reason they do that is that's usually what an engineer is concerned with. How much work can I get out of this system in powering whatever process I'm doing? And so oftentimes they define work exactly opposite, so as the way maybe a chemist or a physicist might. But as a result, you sometimes see this equation written as delta U equals Q minus W, and my apologies if you see it that way, and it's a source of a lot of confusion. But we're going to stick with this and define W in a very specific way, common to usually how chemists and physicists define it. So we're going to run with it. All right, so now we kind of conceptually see what's going on here. So let's talk a little bit more about work. So we're going to look at a special kind of work we focus on typically in this chapter, and we call it pressure volume work, or PV work for short. And we're going to envision having a gas in a cylinder with a movable piston. So and we're going to have this gas expand against a constant pressure, at least in our first example here. And so this gas is going to apply a force against that piston. So, and if we wanted to calculate the work associated with that, well, you might remember that work is equal to force times displacement. Well, in this case, we're going to look at it a little bit differently. We're actually going to look at the work is equal to pressure times the change in volume, or at least it's going to be related to this. We're going to find out it's the negative of this. But if we kind of take a look at the way the units work, well, if you recall, pressure is force per unit area. So, and if I was multiplying that by change in volume, so take a look at this. So change in volume, that's going to be in units of meters cubed. Area is going to be in units of meters squared. And so we're going to have force times meters cubed over meters squared. It's going to be force times some sort of unit of length, which is what we said work is. And it turns out we can come with a completely equivalent expression for work in terms of pressure and volume. And it turns out there's a little more to it than just this. And the way we define the mathematical signs, it turns out it's equal to negative P delta V. At least it is if we're carrying out a reaction under constant pressure. I say reaction or whatever process we're carrying out at constant pressure. Now the negative part, if you take a look, so in this case we talked about if work is being done by the system on the surroundings, that's when work is going to be negative. Or if the work is being done by the surroundings on the system, that's when work is going to be positive. Well, in this case, if the gas is pushing the piston back, the gas is our system in this case, and it's doing the work. It's doing the work of pushing the surroundings back. And in such case, you're going to get a positive value for delta V. Pressures are always positive or zero. They're never negative. So in this case, if delta V is positive, then by the time you factor this negative sign in, that's when work's going to come out negative. And just as we said, when a system does work, the system loses internal energy and your work should come out to be a negative number. And so the sign makes sure that takes place. Now, if we did this the other way around, if we pushed the piston down, notice who's even doing the work here. The gas is not pushing anything. It's we are pushing the piston down. We are part of the surroundings. And so the surroundings is doing the work if it was going the other way around. And if we push the piston down, that's going to compress the gas. It's going to make its volume go down. That would be a negative value for delta V. And a negative value for delta V times that negative sign there would get you a positive value for work. And so when the surroundings do the work on the system, that's when the system gains the energy and work comes out to be a positive number. And so this guarantees it's going to work out that way. Now, if we take a look at what's happening again, and this reaction is done at constant pressure. We'll look at this plot of pressure versus volume. So in the original example, we were looking at an expansion. And so we were going from a lower initial volume to a higher final volume. And ultimately what you're doing in multiplying P times delta V, and we'll factor in again that negative sign in. So, but you're really calculating the area under this curve. If you look, so we've got P right here, and then delta V is just the difference between V initial and V final. And notice this is the area of a rectangle. You're multiplying length times width. Well, the length here, or the height, whatever you want to call it, is the pressure. So, and then the width here is going to be the change in volume, V final minus V initial. And we can see that the area under the curve here, so is equal to the work. Now again, you got to remember that if delta V is positive, then the work is negative, and if delta V is negative, then the work is positive. So, but the area under the curve on a graph of pressure versus volume is equal to work. Now you got to be careful of units and stuff like this. If you use the pressure in atmospheres and the volume in liters, you're not going to get work calculated out in joules in that case. But if you use SI units here and the pressure in pascals and the volume in meters cubed, then yes, this lovely formula would get you the work in joules. Now, it's not always this easy, as we'll see. Now, by taking a look at an example where we did this at constant pressure, we got a special case. And we could see that we were looking at the area that was equal to the area of a rectangle, which is easy enough to find as length times width. But what if it wasn't done at constant pressure? What if we had something that, was at an angle, or wasn't even linear for that case, which is pretty common? Well, it turns out to find the area under the curve, it's a little more complicated than this. And so it turns out work is equal to, the negative integral of P dV. Oh, how fun is that? Okay, so this just got real. A little more complicated than we had just a second ago, but this is the true definition of work in any situation. Well, if we look here, there's a couple different ways we could look at this. Well, one, if you're carrying out a process at constant pressure, and it turns out we'll define that as what we call an isobaric process in a second. So, and I realize this is an algebra, for an algebra-based class, this is just a little helpful. I didn't want to just throw a couple equations out there without showing where they come from, but you absolutely do not need to know the calculus. So, but for those of you that have a little bit of knowledge in calculus, this is for you just so these equations don't just come out of nowhere. So in this case, we got a couple different options. Well, if you're doing this at constant pressure, well, you can pull constants out in front of the integral, and this just becomes negative p times the integral of dv, and you're integrating from v initial to v final as your boundary conditions. And so the integral of dv is just v from v initial to v final, which gets you v final minus v initial, which is the same thing as delta v. And so in which case you're going to get work simply just equal to negative p times delta v, the same equation we just came up with. So if you're carrying out a reaction at constant pressure, ultimately your work is going to equal negative p times delta v. But what if you're not carrying it out at constant pressure? Well, your other option here, if you're not carrying out at constant pressure, is going to be carrying it out at constant temperature. And the problem is this: so if you're working with an ideal gas, has to be key here, but if you're working with an ideal gas and you're doing it at constant temperature, that means your pressure might be changing. And if it's changing, it's not a constant. And if it's not a constant, you can't pull it out in front of the integral sign. But it's not, the variable we're integrating against here is the volume. And so what you've got to do is be able to write the pressure in terms of the volume so you can actually carry out this integral. Well, if you recall the ideal gas law, PV equals nRT allows us to write the volume, allows us to write the pressure is equal to nRT over V. And we can substitute that in right there for the pressure. And so in this case, this turns into negative times the integral of nRT over V dV. And we'll go from there. So in this case, the temperature is constant in this example. So we're not adding or subtracting any moles of gas or anything. It's for a set number of moles of gas. And then R itself is also a constant. And so N, R, and T are all constants in this particular example. And so we can pull them out in front of the integral. And so as a result, this just ends up equaling negative N, R, T times the integral of 1 over V dV. And our boundary conditions are again still V initial to V final. So, and in this case, the integral of 1 over V is natural log. And so we end up with an expression for work equaling negative n RT times the natural log. And again, our boundary conditions were initial to final. And so you could write natural log of V final minus natural log of V initial, but that just reduces down to natural log of V final over V initial. And so now we've come up with another expression for work, and you've got to know when to apply one versus the other. This is the one that works when the temperature is constant, so that you can pull the temperature out in front of the integral. So whereas again, if you're doing this at constant pressure, then we could just pull the pressure out, and that was a much easier integral to solve for. So you really got those two options then. You've really got W equals negative P times delta V, and this one works at constant pressure. So, or you've got negative nRT, natural log of V final over V initial, and this one works at constant temperature. And so now, if you, given the, what conditions you're under, it's going to be one of these two. Now you know which definition of work to use if you're doing a question involving PV work of an ideal gas. So now we want to revisit our ideal monatomic gas. And again, we said before that our translational kinetic energy would equal 3/2 RT. And that for a monatomic ideal gas, that's the only way it had internal energy. So, and as a result, this was also equal to the internal energy. Now, specifically, this was equal to the internal energy for 1 mole. Well, what if you had 2 moles? Well, then you multiply this by 2. What if you had 10 moles? Multiply this by 10. And so we'd multiply this by n number of moles. And so now we've got a little more generic formula for the internal energy of a monatomic ideal gas for however many moles you might happen to have. Now, if you wanted to calculate the change in internal energy, so, well, you just have, the final value minus the initial value, and you'd have n3/2 RT final minus n3/2 RT initial, and you could factor out the T final minus, or factor out the n3/2 R, and then just multiply by T final minus T initial, i.e. delta T. And our expression would just be n times 3/2 times R times delta T. And so now we've got a formula for calculating the change in internal energy for a gas. Nice, convenient, and it depends only on a change in temperature. If the temperature doesn't change, the internal energy doesn't change either. Okay, so now I want to consider a situation where we've got some sort of constant volume process for just a second. So we're going to consider a constant volume process and go back to this first law of thermodynamics equation. And for a constant volume process, there is no work done. So if you look at what a constant volume process might look like again, so you might have a change in the pressure, but the volume doesn't change. And if you look for a straight vertical line, whether it's going up in pressure or down in pressure, doesn't matter, but for a straight vertical line, there's no area under the curve, and so the work is going to be zero. And so for any constant volume process, it doesn't matter, what kind of process it is. If the volume doesn't change, so anything else can change or not change, it doesn't matter. When the volume doesn't change, work is zero. So, okay, so first thing is we're calculating this constant volume process, work is zero, which means that delta U and Q are equal to each other for a constant volume process. And so all of a sudden now, we'd actually have, for a constant volume process, Q would also equal N times 3/2 times R times delta T. So, well, typically the way we define Q is similar to how we did it in the last chapter with specific heat. If you recall, we have specific heat as Q equals MC delta T, and we're seeing some similarities in the way this is structured. So the specific heat was kind of like, also called the specific heat capacity, is the heat capacity per gram of a substance. And since it's per gram, you have to multiply by how many grams you had, so we have to multiply by the mass. Well, in this case, we want a molar heat capacity for a gas so that you can multiply by the number of moles. And so instead of mass, we have moles. We still have a change in temperature, we still have a change in temperature. So, but now we need some sort of heat capacity. It'll be a molar heat capacity, not a gram-based heat capacity, if you will, a mass-based heat capacity, but we still need a heat capacity, and we can see what's left in the equation. That must be that heat capacity. And so if we rewrite this just a little bit different now, we can say that Q is equal to N times some heat capacity times delta T. And in the case of considering a situation where we have a constant volume, we call this the constant volume heat capacity. And so in this case, we can see that our constant volume heat capacity is equal to 3/2 R. And so for an ideal gas, it turns out for an ideal monatomic gas, that is the constant volume heat capacity. Well, it turns out we're not going to do everything under conditions of constant volume. We might do some at conditions of constant pressure. Well, it turns out, so if you notice this is just 1.5 R, it turns out if you do a reaction under constant pressure, the constant pressure heat capacity is always 1 R bigger than the constant volume one. And we could prove that. We're not going to, but we could. It's not too bad to demonstrate. So it's always 1 R bigger than this. So if we got 1.5 R here, 3/2 R here, then constant pressure heat capacity would equal 2.5 R or 5/2 R. Now it turns out this is peculiar to an ideal gas that is monatomic. If your ideal gas is not monatomic, it turns out it's a little more complicated, and these would not be the values of CV and CP. Now again, for any gas, CP is always going to be bigger than CV by a factor of R, at least for any ideal gas. So, but it's not always going to be these two values, and so we got to talk about some more generic formulas for this. So it turns out that CV is equal to F over 2 times R, and CP is going to equal F plus 2 over 2 times R, where it turns out F stands for what we call the number of degrees of freedom. And this is where things get a little bit complicated. So, and where students start checking out a little bit. So we got to talk about what in the world is a degree of freedom in this context, because we can identify degrees of freedom in a number of different disciplines and they mean totally different things. But in this context right here, a degree of freedom is ultimately a way in which a molecule can store energy in one way, shape, or form. So it's a way that you can have the molecule move and change its orientation in the process in some way, shape, or form. So change how it exists in the universe, so to speak. So we'll see how this works. So we start with what we call translational degrees of freedom. And they just deal with translational motion of a molecule. If a molecule moves in the X direction, you'll notice it moving. And it will change, if you will, it's the way it exists in space. As a result. And turns out with translational motion, you can move in the X dimension, the Y dimension, or the Z dimension, 3 different dimensions, 3 different translational degrees of freedom. And any molecule we could ever consider can always move in the X, Y, and Z dimensions, or at least any gas anyways, and we'll consider them having 3 translational degrees of freedom. Now, we also have to consider rotational degrees of freedom. And rotational degrees is when an object rotates. You might have it rotating in one dimension, or you might have it rotating in another dimension. So, and it turns out there's three different axes of rotation you could consider there. Rotating with the x-axis is the axis of rotation, or the y or the z. And out of three possible rotational degrees of freedom, we got to analyze that. Well, in the case of an ideal monatomic gas, so what does an ideal monatomic gas look like? Well, at the molecular level, they exist as single atoms. So, and as a single atom, think of it as just a cue ball, like in billiards. And if you don't know what a cue ball looks like, it kind of looks like this. It's just a white ball. So perfectly symmetrical in every respect. And as it spins, whether it spins in this axis or any of the three axes, it doesn't change its position in space, its orientation in space, the way it exists in space at all. And there's no energy to store that way, it turns out. There's no associated degrees of freedom. Now, for more complex molecules where you have actual atoms bonded together, which is not the case in a monatomic gas, but if you did, we might also consider vibrational degrees of freedom, where the atoms can vibrate, which changes their position, and sometimes you actually get bends of the bonds as well. So we talk about stretches and bends of the bonds being possible, and so you get multiple potential vibrational degrees of freedom. Well, again, with a monatomic gas, we don't have to consider those at all because there's no atoms bonded together at all in a monatomic gas. So, but it turns out that these vibrational degrees of freedom, they're really only relevant at higher temperatures. At sufficiently low temperatures, they just don't really happen. So there's no vibrational transitions, we say, at these lower temperatures. And so there's no different orientations. If you can't move from one of these orientations to another, then there's no change. And so as long as we talk about sufficiently low temperatures, we'll ignore the vibrational ones. And that's what we're going to do for the purpose of this discussion. But note that at higher temperatures, there really are these vibrational transitions for more complex, not for monatomic, but for more complex molecules existing as a gas. Okay, so the way this works then for a monatomic ideal gas, so you only have the three translational degrees of freedom, and so F equals 3. And we can see that, yep, constant volume heat capacity would be 3 over 2 times R, just like we saw a minute ago. So, and again, the constant pressure heat capacity would be 3 plus 2 over 2 times R, i.e. 5 halves R. Not so bad. So what if we have a diatomic gas? And so the next kind of a gas you want to consider is a linear diatomic. So in a linear diatomic, again, now we have atoms bonded together, and at high enough temperatures, we really would have some vibrational degrees of freedom that we're going to completely ignore. We're only going to look at the translational and rotational ones. And again, for any gas molecule, it can move in the x, y, and z directions. That's 3 translational degrees of freedom. So, but we're going to model this linear molecule with our marker here. And we're going to see that as long as we're rotating along those 3 axes, only 2 of them actually change the orientation in space of this marker. One of them is this one. And so if I rotate it in this one, you can totally notice it rotating. It's changing its orientation in space the entire time. Another one is this one, and it's totally changing its orientation in space the entire time. But another one is this one. And you can see it rotating, which is convenient because I want you to see it because there's writings on this marker. But there's no writings on a molecule and things of this sort. And as it would rotate as a linear molecule in this, on this axis, it wouldn't change its orientation in space at all. And so as a result, for a linear molecule, a linear diatomic, it only has 2 of 3 possible rotational degrees of freedom. So 3 translational, 2 rotational, and that's now 5 total degrees of freedom. And so for a molecule like O2, where F is equal to 5, CV is now equal to 5 halves R, and CP is now equal to 7 halves R. So, and again, we're assuming we're at a low enough temperature that there's no vibrational degrees of freedom to worry about. But again, because there are bonds in this molecule, there really would be vibrational ones on top of that if we're at a high enough temperature. And then finally, what if you've got some sort of non-linear molecule? So, and what if we got something like water? So in chemistry, we learned that water actually adopts a bent structure. And so now as a result, again, it's still a molecule. It's still going to be able to move in 3 different dimensions. So that's 3 translational degrees of freedom. But it turns out now, no matter which way you rotate this, it doesn't matter if you rotate this on the x, y, or z axis, it totally changes the orientation of the molecule in all 3 ways. And so now you get 3 rotational degrees of freedom. 3 translational, 3 rotational, 6 total degrees of freedom. Again, if we're ignoring the vibrational ones, but 6 total degrees of freedom. And so for a molecule like water, all of a sudden CV is going to equal to 6 over 2R, i.e. 3R. So, and CP is going to equal 6 plus 2 over 2, that's 4R. And notice once again, though, that CP being 4R and CV being 3R, CP is bigger than CV by R, yet again. Cool, and that's how we'd kind of treat this. Now, most of the time, you're probably going to be dealing with a monatomic ideal gas, but I can't guarantee it, which is why we went to this discussion. But those are the three kind of gases you might worry about, either a monatomic ideal gas, a linear diatomic ideal gas, or a non-linear ideal gas here as well. All right, let's take this a little bit further. One more thing to note then. So now we've got a way to calculate Q under conditions of constant volume. So, and we've got an analogous way to calculate Q under constant pressure. And so regardless of which one you've got, which situation, constant volume or constant pressure, you've now got a way to calculate Q with an appropriate heat capacity, whether it be the constant volume heat capacity or the constant pressure heat capacity. And now for an ideal gas, whether it be monatomic, linear, or nonlinear, you've now got a formula for how to figure out what that value of CV or CP is going to be as well. So now we're going to set ourselves up to be able to do calculations under a variety of conditions of internal energy, heat, and work. And we remember our first law of thermodynamics, that delta U equals Q plus W. So, and we've learned that we've now got some ways to calculate Q under conditions of either constant volume or constant pressure. So we're now going to learn some things about how to deal with the relationships between these three variables under 4 different conditions. And those conditions are going to be an isobaric process. And again, for an isobaric process, it means that the pressure is not changing, it's constant pressure. Or I could say that the change in pressure is 0, there's no change in pressure. So we've got an isochoric process. Well, this one is often commonly referred to as a constant volume process or an isovolumetric process. So keep in mind that the prefix iso here means the same. And so isobaric means the same bar, the same pressure the entire time. Well, for an isochoric, this means the same volume the entire time. So isothermal down here is going to actually mean the same temperature. And so it means constant temperature. So delta T is 0. So then we got the oddball here, and this is an adiabatic process. And an adiabatic process is where whatever container, let's say your system that you're investigating is in, it is completely insulated from the surroundings so that there's no exchange of heat between the system and surroundings whatsoever. And so Q is equal to 0. All right, so let's kind of take a look here at some of the things, deductions we can make right off the bat. Well, let's start with that adiabatic one. We just said Q is 0. And so we're going to figure out what the change in internal energy is for each of these processes, what Q is, and what W is in terms of some simple formula. So and what's nice here, so we'll start with that adiabatic. Well, in that case, that's easy. Q is 0. Life is good. Okay, so let's go to isochoric next. If the change in volume is 0, and we saw just a little bit ago that when the volume doesn't change, there's no work done, regardless of whether it's done at constant pressure or constant temperature or not. So there's no area under the curve of pressure versus volume. And so when the volume doesn't change, the work is 0. And then finally, we found out with an ideal gas that its internal energy is completely dependent upon its temperature. If the temperature doesn't change, the internal energy doesn't change either. And so for an isothermal process, it's the change in internal energy that's always going to be 0, regardless of what else is true. So we'll start there. All right, so let's go to this isobaric process. So let's just talk about Q for a little bit. So we had some definitions for how we could calculate Q just a second ago, and isobaric was one of those. If you have a constant pressure situation, then you use the constant pressure heat capacity to calculate Q, and it was NCP delta T for calculating Q. Now, then we said we also have a situation where you have constant volume, and in a situation where you have constant volume, then you use the constant volume heat capacity instead. And you just got to be able to figure out, the values of CV and CP in each case, depending on if it, again, is a monatomic, linear diatomic, or non-linear ideal gas. All right, finally, we've got Q down here, and we'll talk about that one a little bit separate in just a little bit, but we can see here that if Q plus W has to equal 0 for an isothermal process, well then Q and W are going to have exactly the same magnitude, just one's going to be positive and one's going to be negative. That way they add up to 0. All right, we'll come back to that in just a sec though. So, all right, so now let's look at this change in internal energy. Well, what's nice is we actually already have an expression for the change in internal energy that we came up with just a little bit ago. And again, we said for a monatomic ideal gas that N 3/2 RT, monatomic ideal gas, there's an expression for the internal energy. And for the change in internal energy, it was N 3/2 R delta T, which we then wrote as delta U equals N CV delta T. And this was the change in internal energy. It was totally dependent on having a change in temperature. And that's always a formula that will work for the change in internal energy, and we can just copy it right down the list in any one of these conditions. And so in this case, we're going to have NCV delta T, NCV delta T, NCV delta T, except we don't have it there, except we kind of do, right? Because if delta T is 0, because it's an isothermal process, then NCV delta T will come out to 0. So, I mean, you could write NCV delta T here. You just got to remember that because delta T is 0, then the entire formula comes out to 0 as well. All right, so now we've got a formula for the change in internal energy, and now we go back to work. So we had two expressions for work. The first one we learned was when we had a constant pressure process, and we could pull pressure out in front of the integral. So, and it was just negative P delta V. So the other expression where we had an expression for work is when we had an isothermal process, one where the temperature was constant and the temperature could be pulled out instead, and we had negative nRT natural log of V final over V initial. And so from things we've already talked about, we've filled out most of this chart here. We've only got a couple others to worry about. Now, in the case of the adiabatic process where Q is 0, well, if Q is 0, then delta U is simply equal to W, or W is simply equal to delta U. And so in this case, we have an expression for delta U. Well, then W is going to equal the same thing. And so here, W is also equal to simply NCV times delta T. All right, same thing down here with isothermal. So here, or at least similar thing I should say, so Q plus W has to add up to 0. And so we already have an expression for W. How do we get an expression for Q? Well, Q here is just going to equal the opposite sign of whatever W is. And so in the case of Q, it would just equal positive nRT ln V final over V initial in such an example, which most of the time you'll just see it more commonly written out as just whatever the opposite sign of W is. And now we have a way of figuring out delta U, Q, and W in any one of these four situations. And that's what you've got to be prepared to do calculations with. So let's have a little fun here and see how this works. So we don't have a lot of room left, but I think it's instructive to still have these up there to see how we use them. So first question says 2.00 moles of an ideal monatomic gas is expanded from 0.0500 meters cubed to 0.100 meters cubed at a constant pressure, i.e. isobaric process, of 101,325 Pascal. Calculate Q, W, and delta U. So this is the equation we're dealing with. So in this case, it's instructive to identify it first as an isobaric process and then to realize, oh, for an isobaric process, constant pressure, we've got a very simple formula for work. So, and because it's done at constant pressure, we use the constant pressure heat capacity when calculating Q. So, and then we could either just calculate Q and calculate W and add them together to get delta U, or we could always use this formula as well if we happen to know that constant volume heat capacity and get it from that one as well. Either way should work in this case. All right, so we've got our work cut out for us. Let's start with Q, let's say. So Q is equal to NCP delta T. And we said for a monatomic ideal gas, CP was going to equal F plus 2 over 2, where F happened to equal 3 degrees of freedom from monatomic ideal gas. And so we're going to have CP equal to 5 halves R. So here Q, we had 2.00 moles of gas. So CP was equal to 5 halves R, which is the 8.31 joules per mole Kelvin, and then times delta T, T final minus T initial, and then we run into a problem because we don't have T final and T initial. We'll come back to that. So then we want to calculate the work as well, and in this case we got a simple formula for that, negative P times delta V. So in fact, let me write that just a little bit lower. So we can save a little room to finish the above calculation. So, and in this problem, we know the pressure. It's 101,325 Pascal. Nice, conveniently in SI units. If it wasn't, I would convert it into SI units. And then times the delta V, and in this case, that's just V final minus V initial, and both were given. So in this case, 0.01 meters cubed minus 0.005 meters cubed. I didn't quite have room to get the units on there, but it was in meters cubed, also SI units. And so as long as we got Pascal and meter cubed, work will come out in joules. And this we do have enough info to calculate. Let's let the calculator do the heavy lifting for us. And so 101,325 times 0.01 minus 0.005 in parentheses there is going to get us 506.625. It is negative here. So, and I'll round that to, what is this, 3 sig figs? 3 sig figs, so negative 507 joules. Okay, so far so good. We're a third of the way there. We got the work. We still need the heat. We still need delta U. And the problem we ran into with heat is we didn't know the initial or final temperature, except we kind of do. So we're told these are ideal gases. And we have one big law governing ideal gases. That's the ideal gas law, where PV equals nRT. And if we rearrange to solve for T, so it's going to equal PV over nR. And both for the initial and final conditions, we know the pressure, we know the volume, we know the number of moles, and we know R. And we can calculate both the initial and final temperature. They weren't given, but everything we needed to calculate them out was given because all three other variables in the equation of state were there. And so in this case, with the final temperature, so the pressure the entire time was 101,325. So the final volume was the 0.01 meters cubed, so times 0.01. Divided by 2 moles and divided by the 8.31. And we're going to get a final temperature of 60.96, so essentially 61.0 Kelvin. So, and then for the initial temperature, the same calculation, the pressure wasn't different, the volume was. So N and R are exactly the same, so I'm just going to do second function entry. Go back and replace 0.01 with 0.005 and get a temperature of 30.48 Kelvin, which will round to 30.5 Kelvin. And now we can calculate and finish the calculation on Q there. And so in this case, we've got 2 moles times 5 over 2 times 8.31 R. And then times, in parentheses, 61 minus 30.5. And we are going to get a value of 1267.275. And again, rounding that to 3 sig figs would be 1270. Joules here. And now we have Q and W. Now we could go back here and find the constant volume heat capacity, 3/2 R. Plug in the 2 moles and plug in the same delta T we just got, or we could just say delta U equals Q plus W and just add the two together, which I think is the easier way to do at this point. So, and in this case, we just have 1270 minus 507, and we get 763 joules. Let's just go verify that this works the other way around back here as well with NCV delta T. So in that case, we got 2 moles times 3/2 R. So 3 over 2 times 8.31. And then times delta T. And delta T again was the 61 minus 30.5 in parentheses. And once again, here I get actually 760.365 because in the other cases, I rounded here and I rounded here, and so it comes out just a little bit different, but in principle, coming out to the same value. So, and there we go. We've just calculated QW and delta U for an isobaric process, and along the way, we had to use the ideal gas law. All right, so the last problem we're going to work here says 2.00 moles of an ideal monatomic gas is expanded from 0.0500 meters cubed to 0.100 meters cubed. So far, exact same question we just did. Here's where it changes though. Instead of saying at a constant pressure, it says at a constant temperature of 305 Kelvin, calculate Q, W, and delta U. So now I have to realize, oh, it's done at constant temperature. This is an isothermal process. Sometimes you'll hear these referred to as reversible isothermal expansions and things of this sort. And I won't get into what the reversible part means, but it's an isothermal process. And for an isothermal process, well, right off the bat, we can say delta U is 0, done. Okay. And then we have a way to calculate the work as well as the heat as the negative of whatever we get for the work. And life is good. And here's the deal. There's 4 different situations here, and you're going to have to be able to calculate delta U, Q, and W in any one of these situations. You've got 2 options. you either memorize this lovely chart and how to calculate everything. So, and there's a couple of ways you can do that. You can just make note cards and by chance, try to memorize it. The truth though is that if you work a number of examples along this, it'll just kind of work its way into your head. Now, the other thing you can do though is just get to the point where you're comfortable enough with what these terms mean that you can actually derive the chart, that you can come up with the chart all yourself. You can be like, oh, isochoric delta V is 0. Oh, that means work is 0. Okay, great. So you can be like, oh, adiabatic Q is 0. Isothermal delta U is 0. So, and at least get you pretty quickly to start filling in some of the key variables and stuff like that. But at the end of the day, whether you memorize it or have a good enough understanding that you can derive it, you're going to need to be able to do that. So, all right, let's get back to this. So first off, we can start and just say, oh yeah, isothermal process, delta U is 0, done. Okay, now it turns out not always true for a real gas. If you get in a more advanced class, you might start talking about real gases, but for an ideal gas, delta U is 0 if delta T is 0, so life is good. Then we've got to talk about Q and W, and we've got a nice way to calculate work for an isothermal process. So we derived it earlier with calculus, but again, obviously you guys are not on the hook for any sort of calculus, and so it's just going to be negative nRT natural log of V final over V initial. So life is good. It turns out for an ideal gas that you could also end up looking at this as P initial over P final because pressure and volume are inversely related for the ideal gas at constant temperature. So, but this is typically the way you'll see this equation presented. So, and in this case though, we don't have to use the ideal gas law because the initial volume and the final volume are both provided. We're just going to be doing some plugging and chugging. And so in this case, work equals negative 2 moles times the 8.31 joules per mole Kelvin. And we're told we're doing this at 305 Kelvin. So, and then natural log of V final over V initial. So that's the 0.01 over 0.005. Run out of room there a little bit. So, but you get the idea. And we have a pretty straightforward setup on this one, a little bit easier than the last example. And we'll let our calculator do the heavy lifting here. So we've got negative 2 times 8.31 times 305 Kelvin times the natural log of 0.01 divided by 0.05. All right, that's going to be negative 3513.6, which I'm going to round down to negative 3510 in 3 sig figs. So, and in that case, that makes figuring out Q here pretty simplistic. Q is just the same magnitude, opposite sign, and so it's positive 3510 joules, and we can verify that Q plus W equals 0, but it kind of had to because we used the fact that they added up to 0 to figure out that this one was the positive 3510. So, but that's all there is to it. So we did 2 out of the 4 different situations. I'd recommend getting a little bit of practice under your belt till you feel comfortable with this. If you found this lesson helpful, consider giving it a like. Happy studying.